Okay, so the next problem that was missed pretty often was number 8. And that one is very similar. So it's actually conservation of angular momentum problem again. And it is a little bit intense, and it's kind of got a couple more things happening with it. So let me go over this one with you. Okay, and what's happening on this one is you start out with a disk. All right, you start out with a disk, and let me again make sure I know which one I'm talking about here. You want to know what is the common speed? Yeah, okay, so you start out with one disk that is spinning around. You know everything about this system pretty much. You know the mass of the disk. You know the radius of the disk. Okay, so radius of disk number one is 0.15 meters. Mass is 3.5 kilograms. And you know the angular speed or the angular velocity of this thing is 90 radians per second. Okay, so that's where you start. Where do you end? Well, you drop another disk down on top of the first one. Okay, and I've shown it just kind of so you can see one on top of the other, right? It actually has a larger radius and more mass, okay? But I just drew it on side here so you can kind of see it. Same kind of idea, right? So you basically take a disk and you drop a second one on top of the first one. Now, here's what you need to realize. The axis of rotation did not change. Let me say that again. The axis of rotation, or the spin axis, did not change. So what do we know is conserved? Angular momentum is conserved, okay? So we know this is still true for number 8. Okay, what changed? Well, the mass changed. We get a new radius on top of it, right? We have a second disk on top of the first one. So that also has to change our omega. And in what way does that happen? Well, here's how we figure it out, okay? Let's go ahead and set up the angular momentum formula for the first disk, okay? So for the initial, and I'm just going to call it initial for this one, okay? In the initial case, your angular momentum initial was equal to your I of disk 1, all right, times your omega initial, all right? And that's got to be equal to, again, your final has to be equal to, now this is interesting, it's got to be I omega still, okay? We know the omega here is going to be our final. But what about our I? What do we put down for our I? Because it turns out we have the I of the original disk, but we just dropped a new one on top, didn't we? So here's what you actually have. You don't have one I, you have two summed together, okay? So I'm going to bump this out a little bit. So actually what you have is the I of disk 1 plus the I of disk 2. You have a sum of both of them. Your moment of inertia increased. And you just have your omega final, all right? So this is actually how we solve this problem. This one's equal to that one, okay? So if we find this value first, let's go ahead and set these two things equal. Let's get rid of these L's. We actually don't care about the L at all. We just care about these values in here, right? So L initial is equal to L final. And just to save some space, I'm going to take and what I have here, I'm going to write in for Li, okay? So the initial case, we have I1 omega initial. And for the final case, we have this business here because we can just substitute that in. Okay, so we have I of 1 plus I of 2 times our final common angular velocity. So let's pop in the numbers that we have. Okay, what we have, I1, well, we don't have that. But we do know that the I, the moment of inertia for any disk at all, is 1/2 mr squared. Okay, so here I'm going to put in 1/2. Mass of disk 1 is 3.5 kilograms. Okay, and R for the first disk is 0.15 meters. Now we have to square that because it's mr squared. Okay, so that's our I value here. Our omega value, we've got to multiply all of this by our omega. Our initial omega was 90 radians per second. Okay, so that goes in here. 90. This is kind of going to be a long formula already, right? So we want to simplify that one down. Reduce it down to a simple, easy to look at number, okay? On the other side, what do we have? Well, we have 1/2 mr squared here because it's still a disk. And for the second now, it's also a disk, okay? So we have 1/2 mr squared for this guy also, all right? I'm going to run out of room if I don't do something really quick here. So I'm going to go ahead and erase this up here to give myself some more room, okay? So if you need to, pause it, write what you got down, and transfer it up. Okay, I'm just going to take and write this up here. All right, so on this side I have 1/2, what we already came up with, 1/2 point times 3.5 times 0.15 squared, right, times 90. On the other side, now, I1 didn't change, so we still have this whole business here, okay? This is still on the other side, it's on both sides, okay? So we still have 1/2 times 3.5 times 0.15 squared, okay, times, sorry, and now we have the other I, this is I2. Okay, so I for disk 2, we have 1/2, okay, so for I2 we have 1/2 mass of disk 2, which is 5 kilograms, okay, and radius of disk 2, which is 0.18 meters, 0.18 squared, okay, 1/2 mr squared. This is for disk 2, okay? Now what we're going to have is those things multiplied by our omega final. Okay, so what we really need to do here is now simplify this down, okay? So I'm going to pull out my calculator. You guys can do the same thing at home. And I'm going to figure out the number on this side and make it easier to look at, okay? So for the initial case here, all right. I should be able to do this probably in my head, but you know, that's not happening right now. So 0.15 squared times 3.5 times 1/2 and times 90, or omega initial. And the number I get for that, this whole side here reduces down to 3.54, okay? What do we know for the other side? Well, we're going to have a term we don't know, so we're not going to be able to fully solve out the other side, but we can reduce it down, okay? So I'm going to go ahead and do that. So I get 0.15 squared, and I get times 3.5 times 0.5. So I get 0.039 basically, okay, for the first I. For the second I, what do I get? I have to add in my second I, so I get 1/2 times 5 times 0.18 squared, okay? And for that, I get 0.081, and then don't forget your omega final is still out here, okay? So now I'm going to simplify this one down just so it's easier to look at, and I'll give myself a little bit more room. 3.54 is still the same on this side, and here we get 0.081 plus 0.039. I get 0.12 for both of my i's, my sum of my i's, my moments of inertia, times my unknown. Okay, now that is a lot cleaner to look at. I'm not fully done yet, but you can see now how I'm going to be able to solve for that omega final. So the way in which I did this is really the initial case that you had, total angular momentum that you had, okay, I omega, you only had the I for one disk, and you had the original omega, all right? For the second or the final case, your initial angular momentum has to be equal to your final angular momentum. So we had an omega final. We have a common final speed, but your moment of inertia is actually the sum of both disks. So that's all I did. If you divide this over on this side, you'll find your final omega, okay? So that's it.